Hello, my name is Susan Arnold, and I'm an Associate Professor in the Division of Environmental Health Sciences at the University of Minnesota School of Public Health. Today I'm going to talk to you about the concept and application of the controlling compound for assessing chemical mixtures. The learning objectives of this module are to define the concept of the controlling compound and explain the application of the controlling compound to a chemical mixture in a simple case study using the SDM 2.0. The SDM is used as a vehicle to demonstrate the application of this principle. Learners are not expected to be proficient in using the tool for this module. If you executed a license for the SDM 2.0 tool and downloaded the files, you'll already have the support file. If not, complete the license application process located at the link on the slide. You'll need to register for an account, after which you will be sent a link to download the SDM 2.0 and SDM 2.0 support file. For this module, we'll be using the following chemical mixture as an illustrative example. Let's say I was tasked with assessing exposure to a chemical mixture containing the following volatile chemicals: toluene, xylene, ethyl acetate, benzene, methylene chloride, and carbon tetrachloride at the corresponding weight percents shown in the table. Note that in the table, toluene is presented at the highest weight percent of 40%, while benzene is present at the lowest weight at 2%. The other chemical weights fall in between these two. If the mixture is allowed to evaporate, all of the chemical constituents could evaporate into the room air that could then be inhaled by anyone breathing that contaminated air. I don't have enough resources to measure all 6 chemicals, so how should I proceed? Is it valid to assume that the chemical that is the largest component by weight will have the highest exposure? Should I focus on the chemical with the lowest OEL, most significant health outcome, or on the component that is the most volatile? Do I need to consider all of these, or do I just give up because it's just too difficult? A better approach is to apply the concept of controlling compound. The controlling compound or component of a mixture is the component that will have the greatest likelihood to exceed its corresponding OEL and can be identified as having the highest adjusted vapor hazard ratio or VHR. Note that the terms compound and component are used interchangeably here. Whereas with a pure chemical, the vapor hazard ratio is determined by dividing the chemical's vapor pressure by its corresponding OEL, the adjusted vapor hazard ratio is determined by dividing the chemical's adjusted vapor pressure by the chemical's OEL, which will be discussed in more detail shortly. To assess exposure to the mixture and identify the controlling compound, I will need to know the weight percent of each chemical in the mixture, the corresponding molecular weight and vapor pressure of each chemical. If you were using SDM 2.0, the information captured in the table, the weight percent, the occupational exposure limit or OEL, the molecular weight, and the vapor pressure for each chemical would be entered into checklist 1. Where do I find these data? Well, there are several preferred sources, and a few of them are listed here. Start with a safety data sheet to determine the chemical composition. This information may also be available from your company or organization's internal chemical tracking system. Information on chemical properties, including vapor pressure, are available from the National Institutes of Health, National Library of Medicine, PubChem resources online, or the EPA's CompTox chemical dashboard, also online. Company resources can also be great sources. More information on sourcing information is provided in the InTERACCT training module, Sourcing Information. Note that in SDM 2.0, some of this data is provided. That is, if the chemical of interest is in the embedded database, the molecular weight and vapor pressure fields, shaded in gray, will be autofilled. If OELs exist for the chemical, the user will see the OEL types, values, and sources in the OEL table in checklist 1. OELs set by ACGIH are copyrighted, so accessing these values requires clicking on the Hub button that is on the left of the OEL table. The user selects the desired OEL and manually enters this value into the OEL selected field. Once the required data has been entered, a happy face emoji will appear, indicating that the data can be transferred to the input table and then subsequently transferred for analysis. This data and information are then used to estimate the adjusted vapor pressure of each chemical as a constituent in the mixture. Rayle's law provides a reasonable estimate for nonpolar compounds such as solvents. In the structured deterministic model, this is the default algorithm used with the chemical mixtures. Rayle's law states that the vapor pressure of each specific component of a mixture is reduced proportional to the mole fraction of the component in the mixture. It's expressed mathematically in the equation shown here. Rayle's law, its application, and limitations are discussed in more detail in the SDM 2.0 support file. The application of Rayle's law and adjusted vapor pressure values can be seen in the SDM 2.0 Checklist 1 report page. This page appears automatically after the input data are submitted to the table. When mixtures are water-based or comprised of polar compounds, Henry's law is the preferred algorithm for estimating the adjusted vapor pressure of each chemical constituent. It's described in more detail in the support file, but briefly, Henry's law states that the vapor pressure of each specific component of a mixture is reduced by a constant times the component's molar concentration. The output from applying Rayle's law, again remember that that's the default algorithm for SDM 2.0, to estimate the adjusted vapor hazard ratio that is used to apply the controlling compound principle, can be seen in SDM 2.0 on the report page of Checklist 1. This screenshot captures the full page to help orient you. Next, we'll take a closer look at the values in the table to see how the controlling compound works. Zooming in on the table in the report page, we can see the adjusted vapor hazard ratio and VHR ratio % for each chemical in the last two columns of this table. The role of the controlling compound and the use of the mixture vapor hazard ratio, or VHR, is visually apparent here. Notice that benzene and its adjusted VHR are shown in red, while all the other chemicals and chemical values are in blue. Even though benzene comprises only 2% of the mixture by weight, it is the most likely chemical constituent to exceed its OEL. If the exposure level of the controlling compound is below its corresponding OEL, it can be concluded that exposure to any other component in the mixture will also be below their corresponding OEL. So, if we focused on controlling exposures to benzene in this scenario, the exposures of all the other constituents would be controlled. There is another benefit to applying the controlling compound. If we divide the adjusted VHR of each component of the mixture by the adjusted VHR of the controlling component, this ratio can be used to estimate the exposure level of every other component in the mixture. There are numerous useful practical applications of this that are discussed in more detail in the SDM 2.0 support file. The VHR values of the constituents and the VHR of the mixture overall can be used to identify the required level of control. This is illustrated on the next slide. The adjusted VHR of the entire mixture is the sum of the individual weighted adjusted VHRs, in this case 8.339. This adjusted VHR for the mixture determines the required level of control. That is, the level of control required to ensure the exposures do not exceed their OEL. In some cases, each individual adjusted VHR may indicate that mechanical ventilation is not needed, but the overall sum of the adjusted VHRs of the mixture will indicate that it is necessary. It's not always obvious which component will be controlling. Assuming that the component that comprises the largest percentage of the mixture is the controlling component, in many cases will lead to the wrong conclusion regarding exposures. For example, it can be shown that in a mixture that contains 99% toluene and only 1% benzene, benzene is still the controlling component. Additionally, if the occupational hygienist concludes that the component with the lowest OEL is controlling, it can also lead to the wrong conclusions. This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.